Everybody. Welcome to the Mechanical Engineering Departmental Seminar Series. So today it is my great pleasure to introduce Professor Dongbin Xiu from the Ohio State University. So Professor Xiu received his PhD degree from the Division of Applied Mathematics at Brown University. He then conducted postdoctoral research at Los Alamos, Princeton, and Brown before joining the Department of Mathematics at Purdue University as an assistant professor in 2005. He was promoted to associate professor in 2009 and full professor in 2012. And in 2013, he moved to the University of Utah as a professor in the Department of Mathematics and Scientific Computers and Human. In 2016, he moved to the Ohio State University as a professor of mathematics and an Ohio Eminent Scholar. He received the NSF Career Award in 2007, as well as numerous teaching awards at Purdue. He has served on the editorial board of several journals, including the Science Journal on Scientific Computing and the Journal of Computational Physics. He is the founding associate editor-in-chief for the International Journal for Uncertainty Quantification and the founding editor-in-chief for the Journal of Machine Learning for Modeling and Computing. His research focuses on uncertainty quantification, stochastic computing, and machine learning. Welcome.
All right, thank you, Professor Huan, for the kind invitation, and thank you all for coming. It's my pleasure to be here for whatever reason, the very first time at Ann Arbor, back to the NEV territory. So there we are. But I'm happy to be here at this wonderful campus, and the weather was nice. Is nice today as well. Thank you for the kind introduction. Today I'll discuss this is our new work, as we all do these days. Different aspect of machine learning. This is our adventure into the world of machine learning. I'll talk about data-driven modeling of unknown system with neural network. What else? I will first start with the motivation that this is preaching to the choir here. You all know why we do that. I don't do any of this. I mean, math department, but this is the motivation we have, right? So our goal of scientific computing is to understand and predict very complex systems like this. But what we do is that we have all kinds of models. And models in this case would be for different components of the whole thing. And you can see that smart people have developed and designed all these models for different aspects of physics. And for very complex systems that we are tackling today, our usual approach is to add more physics, right? There's nothing around this. And but the problem with that is what I would like to call that we're kind of at the stage that we're at the point of diminishing return. And just adding more physics doesn't mean that your model is better. And you are just, what it does do is that it makes the model more and more complex and more time consuming to simulate. And at the end of the day, you would end up with modeling like this, and they are different by such vast scale that they are still useful, but the usefulness is, we would prefer something better. But this is where we are sort of hit a sort of plateau that just adding more terms, adding more physics doesn't really pay off much, right? So, but this is where we want to investigate the approach of data-driven modeling. And I would like first to make the point that it's nothing new, right? This from the very early stage, everything has been and always been data-driven, right? So in early days, takes centuries of observation of smart people, very diligently record all these things. And then we have model. Of course, the goal of the model, at least for this talk, is prediction. There are all kinds of things we want to interrogate the model to understand underlying physics, but let's just say prediction is one thing, and one major thing. Along this flow chart, of course, there are two key components. One big key component is that we have to come up with a model. And this is where the smart will come in, sometimes with the help of a drop of Apple, but nonetheless, at the end of the day, we have some beautiful equation. But what we tend to think less at the model is that these days, these are not the model. The model is usually just a piece of computer code, right? So because we have accept the fact that the equations have become so complex, we cannot solve them analytically by our human brain. So we resort to the help of computer. We have all the numerical method to help us to solve this. So that's what I call, at the end of the day, this is the model, right? So, and of course, by having the model, we have all kinds of different errors from numerical approximation point of view, but at the end of the day, this is the model, right? So what we call these days data-driven modeling is just, we already accept the fact that we're not capable to solve the equations. And now we sort of say, we're not, for the complex system we are trying to understand these days, we're not really smart enough to understand the equation anymore. Let's take human even out of this part. So that's what, with a simple flow chart, let's just go from data to the model directly. At the end of the day, if the model does the job for good prediction, that's all that matters, right? So you, at the end of the day, everything is stored in the computer, we can execute the model, interrogate the model, try to understand the physics behind it. That's of course a much different topic on how to interrogate a numerical model. But, so with that said, I would like to start with the basic set of everything in this talk that I have a bunch of examples. Everything starts with some kind of ground truth, and this is the ground truth, usually some kind of dynamic system. We'll have example of PDEs, but the ground truth serves only one purpose, is to generate the data. The data is used for what we call observables. This will be our training data. This will be the only thing, neural network or other things you use for approximation to see. They see nothing else, right? So, and then the truth is also used to generate some validation data so that we can just validate to see how the model performs. So, and as I said, I will discuss a methodology, what we call flow map learning is essentially operator learning. Use neural network, you don't have to. Neural net here is just one method here, it's just one way to accomplish functional approximation, but it's very, very flexible. That's why we use it. And also it's much, much more powerful for high dimensional input. For low dimension, by all means, do polynomial. It works fabulously well. But the bottom line is that our model, when we try to learn, only see the observables. It doesn't see anything else. And then, of course, the model after construction can only predict the observed. So what you observe is going to be what you try to predict. Throughout this talk, everything there will be no noise in the data we generate. So data will be, this is a Lorenz example I have this day. So the data we generate are synthetic data. We don't have noise. If you add noise, it's just reduce accuracy. There's not really fundamental difference in the results. But for this case, because we are trying to understand the basic property of the modeling techniques which keep this noise free, it will be an entirely different thing if there will be noise inherent in the model. Then we're talking about stochastic differential equation. That's an entirely different animal. So that's for another talk. So for this case, everything deterministic, we neglect noise for now. So, but anyway, one big assumption that the data, the observables we have may not be the complete observation of whole things. You may only observe partial information. For example, in the Lorenz equation, what if you only have data on X? Can you observe X, and then can you construct a good model for X such that it is still mimic or predict the chaotic behavior? We know a scalar equation can never be chaotic, but then I will show that turns out this is possible. Having said that, I will start with one example. To put this into context, it's a much simpler system. So this is pretend this is the ground truth. This is the physics. So it's a so-called glucose-induced insulin oscillation. Obviously, it has relevance for diabetes. And that's our traditional approach, I would say bottom-up approach. Again, we try to understand, have a schematic, understand every component, then we make assumption, basic modeling for each component. At the end of the day, we come up with a set of equation. There are many models for this phenomenon. This is the one, just more or less popular one I picked from the literature. And I know nothing about this thing, right? So, but we have this. These involve 4 variables and a bunch of parameters. I think there are 10 to 15 parameters, didn't keep track of that. So this will be the one we use to generate synthetic data as the truth, to train the network and to validate. Right? So what we do here that we try to mimic, anticipate what happened in real world is that in real world, people care about the dynamics of insulin, which is I hat here. So hat means the variables here are non-dimensionalized. So the insulin I is what the people care. And not, I would assume that something else people can can measure in this, which is G hat, is a single parameter, is the initial condition for glucose level. So at the moment you start to observe insulin, what's the glucose level of this individual? And if the individual is sitting or having a meal, the glucose level will be different. Of course, once the dynamic starts, the glucose G would also be a variable in time. So, but anyway, the initial one. So let's assume that then there's a bunch of other parameters. So we put all the parameter 10, 15 from the literature, we generate synthetic data. We're trying to model this, but we are going to assume that since people are interested in this, and this is observable, this will be the only thing we can see. Nothing else can be seen. All right, so this will be the data we pretend that happening in real world. For every initial glucose level G0, you can observe a short dynamic of insulin response. This is, again, is time is non-dimensionalized from 0 to 1. This is fairly short, not many time steps. We're going to try to predict in the future. But then let's just say for different glucose level, initial condition parameter, you can observe different insulin response for short time. You can, let's just say it's a big data problem. You can do all kinds of this, collect all this data here. Right? So then we ask the question, can we create a model for the insulin response and only for this? By only knowing this, not knowing anything about any other variables, all the other parameters, they're all embedded here. They're hidden there. For all practical purposes, you don't even know they exist. So there may be 10,000 other parameters. So this question we ask, can we build a model for insulin response I and I only with help, perhaps I know the initial condition, initial parameter of glucose G0. We know this is mathematically impossible because the whole thing is embedded in the bigger system. It has to close when everything else is known. You cannot build a model for I only. Essentially, you're trying to create that scalar model for dynamic system. It doesn't even have sufficient dynamics, right? So, but we decided to try something. Just try it. So with neural network, it's easy to go TensorFlow, PyTorch, whatever. So we put this network at input. I'm going to put all these. I don't know if you see. Oh, okay. I'm going to put the G0, the initial parameter, the glucose level as a single input in here, because that's what we have data. Then for this data, I would put all these things, trajectory here, in the input here. I will leave the very last one at the output here. Right. So I'm trying to enforce a mapping between some evolution of, where is it? Never mind. Oh, I would enforce a mapping between some trajectory of this based on parameter G0 to the next one. That's what. So now we have this piece of data. Let's repeat this. Since we have many of such data, different G0, different early response of insulin. Let's have all this data. I can do the mean square, very simple loss function. I train the heck out of this network. At the end of the day, I will get the network. This network would create a model does exactly that give me any glucose level G0, give me some early response of I, it will tell me the next one based on this. Having that, I can iterate this. I can bring this one into a new thing and discard this one. I can do a moving window. I can keep iterating in time. So I have a predictive model for future I insulin based on this. It knows nothing else about the parameter. Right? The question, of course, you can always train a network. You can always get some kind of convergence. Question is it good or not? So let's now try to interrogate this model, try to understand its long-term behavior, because we have truth behind it. We use truth to generate data to validate this. Again, the network knows nothing about all other parameters, 10, 15, and other variables. These will be some testing cases. We pick some insulin level here. As you can see, these are round number. We just random pick them. These are insulin, the single parameter G0, and we create early response of this. And this will be the input of into a neural net. It's a single network. After training, we're not going to touch this. We just keep executing this based on different initial conditions of insulin and its associated initial glucose level. And this will be one of these things. There are 6 of them. I believe this is the top one. So what the scale is much longer because this goes to 20 longer time prediction. The dot here means these are the initial input based on here. This is the initial input. Everything after dot will be the future prediction. And the blue is what network tells us. The true, rather the truth from the larger system with all the parameters known. All right. You can see here you have the system reached steady state and the match is quite accurate. Take a different piece of here validation data, do longer term prediction. Again, we have good agreement, but you can start to see a little bit oscillation early on before it settles down to steady state. Once again, everything up the dots are the prediction in the future. You never see that in your training data. And of course, another one from here, the oscillation is bigger, and sometimes it becomes completely limit cycle oscillation again. So you can see again, very good agreement. So now we have this single model. I can just tell the model the initial glucose level, the parameter, give the model initial insulin response, and the model will just start to predict the future right on top of the truth, not knowing anything about the 10, 15 parameter or other variables. It just knows this. So we can play God, and we can really analyze this. Is one thing people like to do this from the literature. They try to understand the bifurcation behavior. So this on different G0 glucose level. So they would measure after the prediction of the system settle down to a stable state. They would put the maximum and minimum. They record these two numbers. So if it's steady state, the two numbers would coincide each other. It's the same number. If it's periodic state, you have the two numbers here. If it's wider, it would be this would tell you the amplitude of the oscillation. And this will be the bifurcation diagram you find in books, a math of biology book. Everything is based on the G0, the initial condition, and at this stage, it will be a steady state. Minimum and max are the same, and then become oscillatory, but wider, bigger amplitude. And then all of a sudden, after this G0, it become another steady state. This is a well-known bifurcation diagram for this dynamical system. And again, the reference is the truth prediction by the neural network. So we can also do a sort of time-dependent input, like say the baseline glucose level changes. So at this point, maybe you have a glucose level. This is multiplied by 10. G0 is 1, and here maybe the individual had a meal, so glucose level all of a sudden jump to 12.5. So anyway, you have this thing. The dynamic will of course be very different as you have different piecewise constant of G0. But the neural net does a very good job in this case. All right. So this just shows you that it is indeed possible to create such a model that's inconceivable in the past, that you can observe something and create a model for this thing only without knowing anything else, even though the variable itself will never give you a closed equation. Right? So in this case, it's literally a scalar model, but it has these rich dynamics that match very well with the truth. So I would like now just tell you that this is not coincidental. We didn't just throw this in there and it happened to work. In fact, it's after several years of work. Before we even do that, we know exactly there's no way it's not going to work. So it started with a simple thing. We started with a much simpler setting that there's no missing variable. We observe everything. So let's see, we have a dynamic system. It's a vector. So of f, let's assume we don't know the f. We don't know the equation. So what we know are the measurement of the state variable, all of them. There's no parameter in this case. So we observe all the states. But we observe them as a trajectory over time. So, and we have many different trajectories. So you have piece of observation, just like the plot I gave you earlier. So in this case, we want to create a model for this system that, when I call model, is that it can predict, given a new initial condition, which may not be in the training set, and it will, over time, the model would predict something just as a truth. So in a way, it's a good model. We never really recover the equation, but as far as the prediction is concerned, it does its job, right? So, and this is a much simpler setting because there's nothing missing. You observe everything, and of course we use neural network. You don't have to. I'm sure you all have some idea of neural networks. This is my one-page introduction for people who really have never heard of anything about. So the way we see neural network is just like mapping. It's nothing but a mapping from input and output. In this case, would be the, I don't know, 2, 4, 6, 8. Yeah, so 8 input mapped to 4 output. So the mapping from 8 dimension to 4 dimension. Everything happening in the middle. I don't know how it works. It's nonlinear approximator, but you train that. There are all kinds of, you probably heard, all kinds of variation network. We use none of this. We use the simplest, fully connected feed-forward network. Right? So anyway, for dynamic system, this is you all heard of the universal approximation theory, guarantee that this approximator can approximate any function on the very, very mild restriction, almost non-restriction. Anyway, so again, back to this simple setting, if you have this thing, so what we try to here is that we're not recovering equation. What we do is that's why we call this flow map based learning, that we're trying to get the underlying flow map. What is flow map? Flow map essentially maps the solution from one state to another state. This is a solution at x t0. This is a solution at x some t, and the mapping in between is measured by the time difference. This is the map. This is called flow map. It's essentially equivalent as the equation. Knowing the flow map, you know how solution evolves. Knowing F, the two goes hand in hand. So not knowing F is the same thing as not knowing flow map. But anyway, also for an autonomous system like this, that when there's no explicit time dependency, only the time difference matters, only the lag matters. We don't really care about time. We don't care the difference between two time states, right? So this is the map we're after, and this is very simple setting. So if I consider a small time lag, let's say 0.1, 0.01, whatever you deem as small, and the solution and the time doesn't matter. I'm going to call time here as t0, doesn't matter. 0 is just arbitrary number. And next one, I'm separating the next one with time at 1 delta t later. So the map in between is also a flow map, parameterized by the time step, right? So this is the time step mapping the solution from one time to 1 delta t later. And this is the map between RD to RD, the same dimension. We don't know this, but this is what we can do, is that if I have data here and 1 step later, I can try to learn the map in between. It's a same dimensional map. It's the easiest thing for neural network to do. So that's exactly what this do. So you can just simply put this in there and make a neural net out of this. And this a little bit motivation on why we do the so-called, also called ResNet. Is not hugely important. ResNet is just, ResNet means that you're not going to, so here, again, we're trying to learn the map between the solution at current time and 1 step later, assume we have the data. So this with neural network, ResNet says you don't need to learn the map here. You can learn the map after getting rid of identity. Essentially, you're going to learn the map between the difference between the two. So it's mathematically speaking, it doesn't do anything. You can just, but numerically speaking, so now the neural network here would be learning this operator, which is slightly smaller because this operator is on the order 1 plus epsilon, if you do simple Taylor expansion. So now you're going to learn something as epsilon. Anything smaller would be, numerically speaking, easier to learn, to train, to approximate. So that's what neural network does. Again, it's not essential. If you don't do that, just simply feed the network here. It works absolutely fine. So as far as this is concerned, then you have, if you have your trajectory data, you're going to feed your current state here. You're going to feed your next delta 1 delta t later as your output, and you can connect network in between. Doing the ResNet just means that you're going to do identity operator. Again, not important. If you don't do that, that's not a problem. Okay. But if you do that, ResNet mathematically doesn't do anything. You're going to create, once after training, this will be the network would be approximating this operator. And then you create, for prediction, you create a scheme like this. Given the current state, you can use network to produce the difference and add this back. You can get the next state 1 time step later, then you can iterate it much forward in time. It will be a predictive model for all time. And this looks very much like Euler forward. And I want to make a strong emphasis, this is not Euler forward, period. Why? Because this scheme does look like Euler forward. It depends on your parameter theta, the hyperparameter in the network training, which you train. The hyperparameter in your training depends on the future states here. So in a way, this is some kind of implicit scheme. It's not Euler forward. Euler forward, everything on the right-hand side only depends on tk, not k plus 1. All right, so because of this little bit of subtle difference, this method is not Euler forward. Not only is that, it doesn't have the error in time t, delta t. It actually doesn't have that term period. All right, so it's in a way, we call this an exact integrator in time without temporal error. So, but it has its own training error, as you all know, if you have trained a network. Anyway, just give you an example, and then that's the error estimate doesn't really matter. It's a simple thing. I want to show you this example. Is this some kind of electrical network? My postdoc put from one of the literature in some paper, but the equation doesn't really matter. Again, we use that to generate syntactic data. The training goes that this thing is happening on nanoscale. So our measurement data is separated by 1 nanosecond. And then this is the prediction of these are 4 variables of V1, V2, this V1 of 1 microsecond, so 1,000 steps later. The prediction, you can see the against the circle and the neural net prediction. The lines are the truths based on the synthetic data based on solving this. I want to make a strong emphasis that here we learn the mapping between 2 states, 2 solution data. The mapping, again, the mapping between 2 states are extraordinarily simple. Again, it's almost 1. Think about a solution T, and T plus delta T is, you do Taylor expansion is 1 plus order delta T. In this case, it's 1 plus order 10 to minus 9. So first, it's very small. And secondly, regardless how the solution looks like, the equation we deal with, I mean, we tend to think complex system as very, very complex. The equation are never complex. Think of Navier-Stokes. It has only a single quadratic term, infinite smooth as far as function is concerned, but it generates all kinds of crazy phenomena, including turbulence, shocks, everything. So similarly in here, in this equation, it is so simple. It's linear, 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 and a single tangent. It's just simple, very nonlinear term, which is hyperbolic tangent is also smooth. I mean, very smooth. So the neural net is really trying to approximate something small and infinite smooth. So that's why it does a very good job. It does not, however, try to approximate the solution, which is extraordinarily common. You look at this solution, this is hopeless to approximate with all these spikes, but it doesn't do that. So that's the biggest difference. And that's what makes this method work. It doesn't care how you approximate the solution because it doesn't even try that. To give a solution, doesn't matter what it looks like, you try to see how can I manipulate this solution to something else. It's 1 plus delta T. That's all it does. Right? So anyway, so that's what makes this method very, very powerful to get high accuracy. Neural net, I would like to make a remark after years of experimentation, is inherently inaccurate. Right? So if you try to get high accuracy, it's very, very hard. But if you try to approximate something extraordinarily simple, like in this case, I can make a case, the mapping embedded here is very simple. You can get high accuracy. All right. So next thing we do is parameter system. This is fairly simple. You just if a measurement, if I have this is in the spirit of UQ, if a measurement has some parameter, if I also know this parameter, I can throw this into my network. Not only I have my state. I keep losing this thing. I have my x and x to the next time this will be. And then I have the parameter here, that's fine, you can do that, then you can do UQ analysis because this, so that's an easy extension. A difficult extension is what if the system is not autonomous, all right? All of a sudden, everything I discussed earlier is not really true because time matters, right? So you cannot neglect time. So, and this is difficult because like I said, we do not want to have time in the input because whatever you do, in your training data, you will get to the future and you will be out of your domain. So I do not want to have time in my input. And that's what we tried very hard to avoid that. So not only we don't know what F is, we don't even know what this, we don't even know how F depends on gamma. But gamma has to be known. Gamma is you have to know the input to analyze anything. You have to know the wind, gas, whatever. It's the only thing that whatever you observe today may not happen tomorrow. Tomorrow will be some new things. And that's why I put a quote here. So that's the difficulty. So in order to cope with this, what we want to do here, we did a little bit manipulation to the exact formula. So if I can integrate the exact equation like not knowing that, but this does exist, right? So what we can do is that we look at things. The mapping, again, the mapping between two current state time to the next time is based on this integral. But if I do a relative, if I fix my coordinate at the current time, everything is based on one time step. And I can parameterize this, if I know this, by some kind of polynomial, let's just say. Right? In one time step delta state, I can be content with quadratic polynomial. We're looking at one delta t. Any polynomial will do a reasonably good job. And then I can translate the problem of not knowing f as not knowing the parameters for this polynomial. So assuming polynomial is very accurate, which is fine, in one delta t, I can make it very accurate. So now all of a sudden I change the problem to a problem with learning f, but learning the parameters. So that's now that with enough training data that we can now just put this polynomial coefficient that I don't know as part of training data. And I can generate data that for known f, we keep having this, then having this net for every known f, I parameterize into polynomial, fit into here, and then map to this. After learning this, okay, this will be a training based on all your training data that you know the f, you know the gamma. Right. So this will be the for gamma. So parameter. So now for prediction, what if I have a new input? Well, for every new input, you can put in the polynomial expansion approximate over 1 delta t, and you fit in the parameter here, you can do prediction. Now you can do prediction for all kinds of gamma that you have not seen in the training data. So this will be some example, very simple example with a simple driving term. It looks ridiculously good, but it's kind of expected, right? You all know that for dynamic system, eventually the long-term behavior follows your UT. So in fact, this is ridiculously good because eventually it follows U, and U will use a quadratic polynomial in every delta t. And the U here is a new source that never in any training data. It's just a new Wendt-Gas, new load function you never see in training data. But it's fun. You know that you can have a polynomial. So that's one thing that allows us to deal with external input in a remarkably better way. But again, this is nothing surprising because input drives that. So the next really big in our mind advancement in order for us to produce this insulin example in the beginning is this. What if I don't observe everything? So we have a dynamic system that we don't know f already is tough. But for all the state variable x, we separate them into two subsets. Z are the ones we actually have data. All right, we observe Z, and W are the unobservables. We don't know what they are. In fact, again, for all practical purposes, you have no idea they even exist. You may be missing 3 variables, you may be missing 3 million variables. You don't know, but the only thing you know is that you may just observe Z, maybe 2 variables. That's all you know. Right? So the goal is that can we observe 2 variables, for example, and create a model for the 2 variables only? So there exists a mathematical formula called the Moritz-Zwanzig formula says you can do that. It does exist. In a nutshell, the equation look like that. It's a dynamic system for the observable 2 variables only. Has one term here you don't know, but this is a autonomous term. But it says that, but this also includes the integral from 0 to t over s, which means t minus s means that you are going to go back from t to 0. So it means that you can have a model for this z only. But you need information of all the past history from the beginning of the time. So, and it depends on this K, which is the memory kernel. Again, nobody knows. So Moritz-Zwanzig formula is exact mathematically. It just is not very practical because nobody knows what R is, nobody knows K is. Right? So there's been a lot of work in estimating K. We're not getting into that because we only use that. Because those work, if you know the dynamic system F, how do you estimate the K? We don't even know little f in 2000. There's no way we get to the K. But that doesn't matter. That's our motivation. The last term is a random noise based on the initial condition, not really important. What we do here is we make 2 assumptions. One is that this memory kernel, so again, minus s means that we're going to backtrack from current time to the beginning t minus 0. Right? So to t equals 0. We say the memory is finite. So if I want to know something today, I don't need to know its state to the beginning of the universe. I only know that it's t minus 2 days or t minus 3 days, 7 days. In climate model, usually you backtrack past 7 days, you're good. So we're going to assume that there's only finite term of memory here. I don't need to backtrack too much. So I'm going to backtrack from t minus 0, which is current t, and to t minus this. So this t capital M is my memory term. I need to backtrack. Right? That's a very reasonable assumption. The length of memory, of course, depends on the system. You have to do some trial and error sometimes. Secondly, if I do that, so we're going to replace this integral to a finite integral. I'm saying it's finite integral. So there exists some kind of approximation of this finite integral based on state within this interval. And that's again a very reasonable assumption because the least you can do quadrature. I mean, you can do trapezoid rule. We are not going to do trapezoid rule. We're going to say that such approximation exists to get you a good accuracy. That's all we need. Right? So this is always true. Right? So, if we do that, we literally translate this Moritz-Zwanzig to this formulation. This stays there at current time, but this integral will approximate as some kind of function depends on current time backtrack a few steps, whatever within this. we know none of it, we don't know R, we don't know F, but that's fine. That's our starting point is we don't know the right-hand side, but we only need these formulations as RS in order to know the future, we need to know the current time, not only the current time, but also 1, 2, 3, a few steps back in the past. And that is what we do. Now this gives us a motivation to a network structure. Now it involves mapping from the current time to the future time. If we observe everything, that's all we need. The +1 just gets you ResNet. But now in this setting, if Z is not your complete set of variables, it's only part of it, you need to involve 1 step back into the past, 2 steps back in the past, and maybe some number step into the past. That depends on your system, right? So the memory can be long, can be short, you have to do some trial and error. You train this, once you have data, the trajectory of data like I showed in your incident example, and you can train this network, and then you can, for any new initial condition, as part of trajectory, you can keep predicting the future. I want to make this emphasis similar to many things we do in here. Even the network is motivated by very clear mathematics. They should do this, do that. Neural net has a mind of its own. Once you train this thing, it doesn't do any of this. It will do the job like doing the prediction right. In between, you cannot interrogate to get more results. It's not more results. We tried it. So, but it's motivated like this. It should be like this. It does the job. That's all it matters. So I want to show you a simple linear system, which is I want to have a linear system very, very hard to predict to learn and predict. Right? Usually linear system is easy to learn because we are using linear method. Neural net is non-linear method. Actually, dealing with linear system is not that easy. But anyway, this is a system with 20 variables. So dx/dt equals ax, a linear system with 20 variables. We're going to pretend and we split this variable into 10 and 10. We're going to pretend we know 10 of them. P, we have data of 10 P's. We have no idea what the other 10 Q. We have no data, no knowledge whatsoever. So we want to use neural net to create a model for the 10 variable P only. As you can see that it's not, if you don't know Q, there's no closed model. But here, if we involve a little bit of memory, you actually have a closed model for P and random plot you P3 and P6, the 10 of them, right? So in this case, the memory is very short. If I remember correctly, it's 2.4 seconds, if you call it second. Once you have 2.4 seconds to start, the network will somehow knows the entire thing. All right, so and you can see the true value, the prediction, everything match very well for very long time integration. Right? So this is one thing. That's fun. And that another would be a very interesting one would be something like a multi-scale system. This is a much simpler multi-scale system. So the true system would be 3 slow variables, 1 fast variable. Again, I think I have a type of report. But anyway, when absolutely very small, you can homogenize, get rid of this. You would have a closed homogeneous system for the slow variable only. That's a mathematical approximation. It's good when epsilon goes to 0. What if epsilon is fairly small, but not so small? Then this model is not so accurate. But here we can learn the model. So assuming you can only observe slow variable, fast variable are very hard to observe, right? So if we have data on x1 to 3 from the truth, then we're going to train the model with memory for the the x1 to 3 only, and we predict this not knowing anything about y. So this will be the prediction. So the truth would be, it's hard to tell. Truth would be for x1 to 3 looks the same, would be the black. And the neural network is the red. The reference, in fact, is the mathematical equation and homogenization. So you can see here, visually speaking, red and black match much better than the green. Right? So, and I mind you, this is a very, very long time integration. I didn't even plot the first 200 because you plot that the whole thing is clustered. You cannot even see that. But the error-wise, you can plot the error against the truth of L2 error. So the neural net prediction of the X over long time integration states more or less here. A surprising phenomenon happens all the time. We don't really know the error behavior, it doesn't go. This is something we're used to. I mean, any linear method, the error grows over time. This is from the mathematical approximation. This is neural net numerical approximation. So error is much smaller and it's bounded, right? Let me show you also some chaotic systems. So this is Lorentz 63, it's 3-dimensional. Like I said, we try something like, what do you have data of X and X only? Or maybe just 2 variables. I'm going to show you only 2 variables because 1 variable, nothing to plot. It's just one thing. So with 2 variables, so if we observe X and Y, and you're going to create a two-dimensional model for X and Y, not knowing anything about Z, you can still plot. I think which one is correct? Which one? This is reference. This is neural network of the phase portrait of X and Y. And mind you, this is the two-dimensional system. You are not supposed to have chaos, but somehow it knows there's missing things. You will produce this thing just look like this the two-dimensional part of the three-dimensional system. This is the two-dimensional system, and you can compute all these measurement correlation dimension, approximate exponent, the absolute exponent of the two systems. They are reasonably close. The numbers are not as great. Some of them not so, but not that close. But these numbers are hard to get. These are like getting Fourier coefficients from discrete series. Even the same thing, depending on length and number of points, this number would vary. So it's very hard to get this number to some stable state. So, but based on this, we're content at least a two-dimensional model for X and Y give you more or less visually very correct chaotic behavior. So let's make this even more extreme. So we make the Lorentz 96, and which has 40 variables. It's a system of 40 variables only, and let's assume we only observe X1, 2, 3. And let's create a X1, 2, 3 model for a big 40-dimensional model. Again, this is the neural network for X1, 2, 3. This X1, 2, 3 put from the 40-dimensional system. This is very hard to tell. Okay, they look chaotic enough. This measures of chaos, how chaotic system is. This looks reasonably close. I mean, not too bad. You can put a histogram of things. Again, this is a much more complex system. They look reasonable, right? So I think that's all I want to say about dynamic system. Let's move to a slightly different topic. Much more is that how do we do this for PD? So these they are all ODEs. Right? In fact, this is something after the very first work of the fully observed system with ResNet. The first thing we did was, let's do PD. Because why? Because if that's unknown PD, if we have a set of grid, then I have measurement, I have a data on my grid. I'm not missing any variable. I'm going to observe solution at every grid point, and I can put this into a big vector. Then that means I have vector over time. So we have a vector trajectory of vectors, and then I can map this in current time and one time step later. That's exactly what we did for the dynamic system. It's just a vector. It's just this vector may be a lot longer after discretization of PD. So it should work. And that's the first thing we tried. And it just didn't work. I mean, it worked to some degree. It just never satisfactory to my standard, to be honest. It works okay. And we cannot never get this consistent to be accurate. Like I showed you early results, everything is just almost on top of each other. We can never get this thing to be on top. They are always reasonably accurate. But so we struggled with this for almost 2 years. Eventually, we realized if we do the dynamic system work, so we're going to connect a network in between the solution vector here and here. The network dynamics doesn't know any continuity smoothing of your data. Here is a solution PD. That's regularity. This is not just vectors. They're not arbitrary vectors. They are continuity, they're smoothing, dictated by whatever operator you have in your governing equation. One has to embed a way to somehow enforce some connection in your solution that to reflect the operator in your equation. So with that, we try the convolution thing that not there. So eventually we're forced to really design the network. And you again come from a very simple motivation. Again, have an equation like that. I don't know differential operator, but I say I'm kind of stupid, but I can do Euler forward. I can always do that. Let me say I can do Euler forward. It's always, I don't care about stability. It's a one-step Euler forward. It will look like this: a current state delta t with unknown operator, but then inside there is all kinds of differentiation operator. And in my numerical scheme, this can be matrix vector because this is what's called differentiation matrix over the grid. I mean, this new standard numerical analysis, it always exists. So a typical Euler forward can be expressed in this way. If this is good, I can say I can make this more general. I can make this matrix vector product is a mapping. Why don't I make this a nonlinear map? There's nothing wrong. I just make this much more general idea. We just say, okay, if Euler forward has some kind of error like this, then there exists a map scheme like this with this being a nonlinear mapping. that does the same job, at least the same error. Of course it is. I can just reduce this to the matrix, I will get exact truncation error. So if I make this operator nonlinear, I potentially can do even better. So that I don't really care. We just say I can make that exist a mapping between current state and next state with some unknown operator correspond to L, I don't know, but with some operator here, I don't know, but each one corresponds to a differential operator. It exists. That's all we need. So that's only serve as a motivation. We're not going to use this to solve anything, but everything is unknown. But now we have measurement of current vector, one step later vector. I'm going to put a network in between to reflect that there are certain operator here and of here on each solution vector. And there's another operator to operate on the entire thing. This eventually motivates us to do this network. So with the current vectors at the current state and one state later, we're going to have a network here operating on this in parallel, each one representing a differential operator kind of. And this will be the F here, F1 to J. And then I have a network here component-wise on every single operator that would somehow represent this M here. And this would give me something correspond to exactly this thing. This network would do this. And then we're going to map this back and then do the ResNet to reflect it +1. That would work. Turns out indeed it works. Right? So existing, of course, guaranteed because this network does exactly that. And we know this thing exists. Again, it's not all forward because it's by training. It depends on the future. It doesn't require structure, which is a good thing and sometimes it's a bad thing because now that I have my solution vector here and here, these are at the grid point. I don't need to know how the grids are connected together. As long as the grid has exact ordering here, it will do the job. All right. So, and let me show you a couple of examples. We'll be done with that. This is a simple advection diffusion equation. Again, this is a very, very difficult system to solve for long term. Advection diffusion is perhaps the simplest analytical equation to solve analytically, is the most difficult to solve numerically. But anyway, we can rule this. Again, these are syntactic data, train this, learn this over time, in a fairly long time. The prediction is quite close, actually much better than we anticipated. Advection diffusion is easy. I want to show this. This is where we can have so the points represent the grid. They are non-uniform. They're perturbed randomly. On top of that, the grid sequence is permuted randomly. We don't really care how they order, as long as the ordering are the same from the input and output, you would do the job, right? This will be interesting. I said this is for PD, but doesn't really matter. All you need is have the layer to represent some operator. So you could have an integral operator. This will be actually make this a non-local problem. For this thing decay, so nothing goes wrong. When things decay, everything works much better. But what if it doesn't decay? So this would be Burke's equation. I want to emphasize when we learn these things in general synthetic data, we do not use shocks. Everything is based on randomly construct sine cosine functions. They are smooth, and we only need to solve our training data is only separated by 1 delta t. I think here is 0.05. 1 delta delta, there's no shock. Right? Everything is smooth, but once the network learns the mapping between the solution, and as it moves forward in time, at some point the network will say, oh yeah, the mapping keeps mapping, and then it will produce shock. Right? So you do not, so like what I have to say that during the training, in your training, you do not need to see the physics to produce the physics. You only need to see enough that your network would produce an exact one-step mapping. So then this will produce sufficient intrinsic physics in the future. Just like when we develop the equation, it's all based on simple principle of conservation of mass, momentum. When you develop the equation, you don't know there are shocks, right? Once the momentum is conserved, you have the equation, and later you can find out this has shocks. Right? It's very similar to that. We can do two-dimensional thing. This will be simple advection diffusion over unstructured grid. I think these are quasi-Monte Carlo points with some clustering towards boundary. Again, which one the prediction, this network, this is at different time, this is reference, doesn't really matter, it's just a color picture. This would be interesting. So again, for PDE, we can also say, what if I'm missing variables? So now in this case, is a two-dimensional example, or it's we do not know anything about W. So one set of variables are completely unobserved. So again, you can only observe V, somehow create a closed system by itself. This will be, again, long term. This will be a periodic state that the bubble will just keep going up and traveling in the vertical direction. And the reference of predicting after fairly long term integration, I mean, visually they really agree fairly well. So there are lots of other things we also tried. In fact, this also works. What if we only observe in a partial domain, like half the domain I have data, the other half I have no idea what happens. Actually, for the example we're doing now, it works very well. We're just wrapping up the paper on observing things on partial domain. This requires memory. So this requires you to have to know the past memory. This is a very expensive training. It's two-dimensional, much. Remember the grid, yeah, every grid is the number of input, and with the memory, I think this has like, I forgot, 25 by 25 grid. And then with memory, you just double, triple. This takes time to do that. But anyway, there must be a way to speed this thing up. But at this moment, we haven't got the time and energy to deal with that. We just did things in the most straightforward way. So as I said, this will be a fairly summary of what will come. So the early example with the insulin example is not in this. It's a serious development. Eventually, as I said, we tried the insulin example. We knew it's going to work. There's no way it doesn't work. We have done much more complex systems. So looking ahead, we have never done anything with real data. So like we don't have real data, so we use synthetic data, which is fine. Noise are not a big deal. Like I said, if you have stochasticity naturally inherent in the equation, that's a very different thing. We have very limited result on that, but so far I think we have made sufficient progress to start this. The standard, every method we develop here just doesn't really work well with stochastic differential equation. I want to make a remark that except the PDE, where we are forced to have a layer to map to the operator, we don't really have network structure. I mean, that's a question sometimes I guess you don't have structure. It's just because why? Every time when things didn't work, we try to identify where it didn't work. Is it the data, is it the training, is it the setup, and here and there. Once we fix everything, it just works. So there's no need to go with structure, so convolution or not. But anyway, and the network are not big. So usually for the dynamic system, we have 3 layers, 30, 20 nodes per layer. They're very simple network. Like I said, the one-step mapping of the operator is extraordinarily simple and very close to 1 plus delta t, and very simple. You don't need big network for that. So with this, I think I will just conclude and open for any questions.
Remarkable results. So 2 questions. One is, does the number of steps that we need to train, does it depend on discretization? I mean, the spatial discretization. So that is, if you have a larger domain,
do you worry about stability, right?
Stability as well as like, do we need more time for the model to figure out like maybe all the fundamental modes or like, other things that are going on in the domain?
Good question. We have not thought too much about this. Right now, how we design time step is that when synthetic data, we will plot this thing, we'll pick a delta t such that when we plot this, it looks reasonably smooth, right? It captures the time scale. That's our only criteria now, just capturing time scale visually. If we plot this thing, or it's little zigzag, or it's too coarse, we make this smaller. So that's the only thing so far, only criteria we used. I don't know how for different systems it's a good question. I don't have a good answer for that.
It may be interesting to see, like, I mean, if you take a larger spatial domain, like if the number of time snapshots you need to train would also.
Right. So yeah, that would be interesting. We did not look into that. So right now, again, it looks reasonable. That's all we try. Yeah, the PDE thing, yeah, it's a little expensive. It's early. We haven't investigated that much yet.
And the second question is, I mean, all the examples that you have shown, I presume, very good success stories. was there a system like where things didn't work out as well as you would have anticipated, or so far, like, you have not come across any systems which.
So for the PD is early, we did this equation. For the dynamic system, I think in the setting I discussed here, they all work. It just takes a lot of effort to identify where things could go wrong. It's never the network. I tell you that's why we never have it's always work. I think if you train hard enough, which is highly non-trivial, I spend so much time with my student postdoc looking through. I like to say in the past 5 years, no less than 10,000 results. You can always find a way to make them work. There are a few things we tried, they didn't work, but it's just too hard. The one thing we tried was the speak of missing variable. We tried model for the daily temperature of Fort Collins based on data from the last 300 years. And we tried to predict that. It never really worked. Then we realized the daily temperature is such a coarse measurement, it's not continuous. So we ended up writing a paper how to deal with coarse time measurements. So that didn't work. Another thing we didn't work was collaborative.
Not a dynamic system. That's very, very complex system.
I know, but we were ambitious, right? You observe this one variable, let's try that with enough memory. Can we do that? We tried that. So it didn't work. Fine. That exactly as you said, that's too complicated. If it works, I think I told our collaborators that, this will be impossible. Let's try it. It's like when you buy a lottery, now you're not going to get it, but you can buy it anyway. So it didn't work. So that's because the system is too complex. Another thing we tried was the combustion problem with multi-scale. We couldn't make it work. That thing, nothing happened. It happened in 10⁻12 seconds. It just nothing happened. We could not capture that. Period. I think that's because the system is too complex, and then they also have adaptive time stepping, ranging from 10 to the +2 to 10 to -14. We couldn't handle that. That made us to try to work on how to deal with adaptive time stepping. Maybe not that extreme, maybe we haven't got anything yet. So far everything is on constant time step. But for reasonable this kind of thing, they always work. I'm not that I want to oversell this. I haven't thought anything we tried reasonable, we've made it work so far. Let's just put it that way. Yeah, maybe the next one comes, it will not work.
Yeah, so very interesting talk. Thank you. So the first question is regarding the comparison between your method and the conventional incident quantification method, including the Gaussian process method for computer experiments. So because you're from you have the experience in Los Alamos lab, so I assume that you know the work done by Dr. Higgin on the emulation of the functional data. So in their work, they just use a spline or dimension reduction method to reduce the dimension to the feature space and fit a Gaussian process on it. Yeah. So, I understand that their method may not be applicable to the missing data part, but given the full data, I'm just curious about whether there are any comparison.
I would say Gaussian process people mostly use that to approximate function, right? It's a surrogate model emulator, as you said. And I'd like to make a point here. Here, the network is not used to approximate function period. It only try to approximate the mapping between two functions, and the two functions being separated by 1 delta t in case of everything observed. So, in that sense, they are used in very different ways. If you ask the question, can I use Gaussian process to approach this mapping? I say yes, you can, because for the low dimensional dimension, we actually use polynomial. It works fantastic. But in high dimension, it's just not, we have to go neural network. We actually, our very first paper was by using just polynomial low dimension, 2, 3, 4 variable dynamic system, polynomial period. Immersion accuracy, everything. So I think Gaussian process, similar thing, that the high dimension is to get a bit more expensive. But yeah, I am not aware anybody trying. So I think that's somewhere you can try. So like I said, you don't have to do neural network. It's just one thing to approximate the mapping. Yeah, anything would do.
Yeah, and one additional question on this topic is that have you attempted any uncertainty quantification through this neural network, say Bayesian?
Oh, we have not. So
okay, thank you.
At the moment, I haven't got the energy to get to that. Yes.
Thanks.
The other, yeah.
So, have you ever looked at for some of these systems, like I know like DMD has gotten a lot of fraction in some of the fluids community and, or maybe like some
Right.
where you have like really high dimensional data, but then you do like an autoencoder and build in the dynamics in like a latent space and a reduced
Right.
setting. Have you looked at those?
So I looked at DMD. I'm very aware of that. We tried that. So these are different, right? DMD is trying to create a best linear approximation. And that's on a higher level philosophically, everything is nonlinear. How far can you go with linear model? That's the question. But I think I want to be fair that the linear model has its advantage. If you can create a good one, it's fast, it's accurate, it's gold. So there's nothing wrong with that. So in that sense, this is very different. This is nonlinear mapping. So actually DMD very similar to this. One step later, you put a matrix A in there. Here you just put a neural network in there. That's the only difference mathematically. In principle, they're same. But sorry, the second part is the latent space, reduced order modeling. I don't know. So we tried that. So if we try that, especially in the context of PD, the vector subset long vector. In fact, you probably didn't notice when I have the structure here, we already tried. This is our way to reduce to latent space and grow in the back. In our paper, this layer is not there. It's the same length. We don't have dimension reduction. We actually spent some time on this. We didn't get anything. So that's right now. Yeah, I don't know. Yeah, thank you.
So you showed one problem, I think, with the fourth order operator.
Right, yeah.
So are you seeing in your structure, in the architecture, are you seeing any evidence of it struggling or needing is it getting deeper or wider as it goes to higher order operators, right?
No, we didn't. So a very good question. So when I didn't say that. So when I say that we have this many parallel layer to mimic this operator, that's already saying, oh, if you know how many operators there are, in principle, if we don't know anything, we don't know. So assuming that if I have, let's say, 5 operators in my equation, what if I only have 2 layers here? Well, you're just going to get the best approximation based on 2 layers. So even if I know for you ask fourth order equation, 2 equations, that there's only 1 operator, I only need 1 thing here. And we actually try that. The first thing we try that, we look into this layer to see if this operator is not. So like I said, the neural network is motivated by this way, but once you train it, it does its own thing. It's never the operator. And we tried very hard to this. And in one way, we can reproduce the operator is that we make this single layer here. We know exactly the second DXCT second order or fourth order. We make this single layer, we make activation function linear. So essentially we make a matrix vector product. Then it produces final difference. But the moment we make this nonlinear, it's all over the place. This layer, we cannot understand what the actual operator is from the network structure. We just cannot read anything out of it, but it does a job. So we have a good intention, but it does the thing. But once you train this thing, it's all over the place. We cannot interpret much out of this, out of the trained structure.
Well, we are out of time. Everybody, please let's thank our speaker once again.
Oh, it's a thing. Yeah, okay. All right.
Thank you very much, Professor Xiu, and thank you everybody for coming.
All right,
We'll see you next time.
Yeah, it's actually exactly the same. Yeah, you don't. It's the same question. Yeah. So, right. Yeah, you do that.
Thank you.